Time is one of the most mysterious and fundamental aspects of our reality. It governs everything from the motion of galaxies to the beating of a human heart. Yet, despite its omnipresence, time remains one of the least understood concepts in physics. Is it an illusion, a fundamental property of the universe, or something even stranger? While we experience time as a steady flow from past to future, scientists have uncovered clues that suggest time may not be as straightforward as it seems. Black holes add an even deeper layer to this mystery. These cosmic monsters, formed from the remnants of collapsed stars, are some of the strangest and most extreme objects in existence. Their gravity is so powerful that not even light can escape, making them the ultimate traps in the universe. But beyond their ability to consume matter, black holes also seem to warp and bend time itself, distorting the fabric of space-time in ways that defy our everyday experience. Near a black hole, time slows down dramatically, and at the event horizon, the point of no return, time may even stop altogether from an external observer's perspective. Black holes are not just fascinating for their bizarre effects on time, they also push the boundaries of physics itself. They represent the edge of our understanding, where Einstein's general relativity collides with the strange rules of quantum mechanics. The paradoxes they create challenge our most fundamental scientific principles, forcing physicists to rethink the nature of space, time, and even reality itself. Some theories suggest that black holes might be cosmic shortcuts leading to other parts of the universe or even other dimensions. Others propose that black holes hold the key to unlocking a deeper hidden layer of physics that could explain the true nature of the cosmos. By exploring the connections between time and black holes, we are delving into some of the most profound questions in science. What is time really? Can it be manipulated or even reversed? What happens inside a black hole? And could these strange objects be revealing secrets about the origin and fate of the universe? As we venture into these mysteries, we find ourselves on the edge of physics, standing at the boundary between what we know and the vast unknown. Time is something we take for granted, but when we try to define it, we quickly run into deep philosophical and scientific challenges. Is time a real, tangible thing, or is it merely a construct of human perception? Does it flow like a river, as we seem to experience it, or is it an illusion created by our consciousness? In classical physics, time is treated as an absolute, unchanging background against which all events take place. Newton believed time was universal, ticking at the same rate everywhere in the universe. But Einstein shattered this notion with his theory of relativity, showing that time is not a fixed entity. Instead, it is woven together with space, forming the four-dimensional fabric known as space-time. According to relativity, time can speed up or slow down depending on gravity and motion. A clock on Earth, for instance, ticks slightly slower than one in orbit, a phenomenon confirmed by GPS satellites which must correct for this time distortion to provide accurate positioning. If time can be stretched and compressed, does that mean it's not real? Some physicists argue that time is merely a human construct, an emergent phenomenon arising from the way we experience changes in the universe. Others believe time is just another dimension like space, meaning that the past, present and future all exist simultaneously, an idea known as the block universe theory. Quantum mechanics further complicates our understanding of time. Unlike relativity, which describes time as continuous and smooth, quantum theory suggests that at the smallest scales, time might be discrete, made up of tiny, indivisible moments. This hints at a deeper, undiscovered theory that could reconcile quantum mechanics and gravity, perhaps a quantum theory of time itself. Some radical theories even suggest that time, as we know it, does not exist at all. Instead, what we perceive as the passage of time may be a side effect of entropy, the tendency of the universe to move from order to disorder. According to this perspective, time's arrow, the fact that we always remember the past, but never the future, emerges from the second law of thermodynamics, rather than being an inherent property of the universe. But if time is just an illusion, what does that mean for black holes, where time appears to stop? what happens to objects that cross a black hole's event horizon? And if time can be altered or slowed, is time travel a real possibility? To answer these questions, we must explore the interaction between time and the most extreme objects in the universe: black holes. Black holes are the ultimate time manipulators. These mysterious objects, formed from the collapse of massive stars, are so dense that their gravitational pull distorts space and time in ways that defy our everyday understanding. According to Einstein's general theory of relativity, gravity is not just a force, but a warping of the fabric of space-time. The stronger the gravitational field, the more time slows down for an observer within it. Black holes are the ultimate time manipulators. These mysterious objects, formed from the collapse of massive stars, are so dense that their gravitational pull distorts space and time in ways that defy our everyday understanding. According to Einstein's general theory of relativity, gravity is not just a force, but a warping of the fabric of space-time. The stronger the gravitational field, the more time slows down for an observer within it. Near a black hole, this effect becomes extreme. Imagine an astronaut falling toward a black hole while a distant observer watches from afar. To the astronaut, everything seems normal. They continue to fall toward the event horizon, the point beyond which nothing can escape. But to the distant observer, the astronaut appears to move slower and slower as they approach the event horizon. Eventually, the astronaut seems frozen in time, never actually crossing the threshold. This is known as gravitational time dilation, where time slows down due to intense gravity. For the astronaut, however, time flows normally from their own perspective. If they were to glance at their clock, it would tick at a regular pace. But if they looked back at the universe outside the black hole, things would seem to speed up dramatically. Galaxies would age rapidly, stars would be born and die in an instant, and the entire universe might evolve before their eyes in what appears to be seconds. This bizarre time-warping effect means that, in a way, black holes act as natural time machines, allowing observers near them to experience time differently from the rest of the universe. But what happens inside the event horizon? According to general relativity, once something crosses the event horizon, it is pulled inevitably toward the singularity, a point of infinite density where the known laws of physics break down. Time itself ceases to have meaning here, as all paths through space-time lead to the singularity. No force in the universe can stop this descent, not even light, which is why black holes appear black. The existence of singularities raises fundamental questions about the nature of time and space. If time essentially stops inside a black hole, could black holes be gateways to other parts of the universe or even to other universes? Some physicists speculate that black holes could be connected to white holes, hypothetical objects that spew out matter and energy instead of sucking it in. Others suggest that inside a black hole, space-time may fold in on itself, creating wormholes, shortcuts through the universe that could, in theory, allow for time travel. However, these ideas remain speculative, as our current understanding of physics breaks down at the singularity. To truly understand what happens inside a black hole and how it affects time, we need a theory of quantum gravity, a framework that merges quantum mechanics with general relativity. Could black holes hold the key to unraveling the true nature of time? To answer this, we must delve into the paradoxes and mysteries at the edge of modern physics. Time travel has long been a staple of science fiction, but black holes may offer a real possibility, at least in theory. The warping of space-time around a black hole creates conditions that could potentially allow for travel to the past or future. One of the most intriguing ideas comes from closed time-like curves, or CTCs, solutions to Einstein's equations that suggest time loops could form under extreme gravitational conditions. If such loops exist, they might allow an object to return to an earlier point in time. One famous proposal for time travel involves rotating black holes, also known as Kerr black holes. Unlike static black holes, which only have mass and gravity, Kerr black holes also possess angular momentum, meaning they spin rapidly. This rotation twists space-time into a swirling vortex around the black hole, creating a region known as the ergosphere. In theory, an object entering the ergosphere could be slingshotted out at speeds faster than light if it follows the right trajectory, allowing it to emerge at a different point in time or space. Some physicists believe that if a traveler could navigate the extreme forces of a Kerr black hole, they might enter a wormhole, a hypothetical tunnel connecting distant points in the universe, possibly even different eras in time. However, even if black holes could act as gateways through time, major obstacles stand in the way. The grandfather paradox, where a time traveler could alter the past in ways that prevent their own existence, suggests that time travel might violate causality. Some physicists believe the universe prevents such paradoxes through mechanisms like the Novikov self-consistency principle, which suggests that events must always be consistent and prevent contradictions from occurring. This means that any action taken by a time traveler would have already been accounted for in history, making true alterations impossible. Another major hurdle is the instability of wormholes. Even if a Kerr black hole led to a traversable wormhole, it would likely collapse instantly under the influence of gravity. To keep a wormhole open, some form of exotic matter with negative energy density would be needed. While quantum mechanics suggests that such matter could exist in the form of Casimir energy, no practical method for stabilizing a wormhole has been discovered. Despite these challenges, black holes continue to be at the forefront of discussions about time, space, and the fundamental nature of reality. If we ever develop a theory of quantum gravity, it may reveal whether black holes truly hold the key to time travel. Could future civilizations harness these cosmic giants to manipulate time? Or are the paradoxes and extreme conditions too great to overcome? The answers lie at the cutting edge of modern physics. Black holes represent the ultimate testing ground for the most fundamental theories in physics. They sit at the crossroads of general relativity and quantum mechanics, two of the most successful yet seemingly incompatible frameworks in modern science. If we are to ever uncover a theory of everything, a single equation uniting all forces of nature, black holes may be the key to solving this cosmic puzzle. Einstein's general theory of relativity describes gravity as the warping of space-time by massive objects, and it works flawlessly on large scales. However, when we try to apply it to the extreme conditions inside a black hole, specifically at its singularity, the point where all its mass is concentrated, the equations break down. This is where quantum mechanics, the theory governing the smallest particles in the universe, should take over. Yet quantum mechanics and general relativity do not agree with each other when describing black holes, creating a fundamental conflict in physics. One major mystery is Hawking radiation, proposed by physicist Stephen Hawking. According to quantum mechanics, black holes should slowly emit particles due to quantum fluctuations at their event horizons. Over time, this means black holes should lose mass and eventually evaporate. But if a black hole disappears completely, what happens to the information that fell into it? This is the heart of the black hole information paradox, a major problem for physics. Quantum theory insists that information cannot be destroyed, while general relativity suggests that it is lost forever. Resolving this paradox is crucial for finding a quantum theory of gravity. Many physicists believe that black holes may offer insights into string theory, one of the leading candidates for a theory of everything. String theory suggests that all particles are made of tiny vibrating strings, and that extra dimensions beyond the familiar three of space and one of time exist. Some versions of string theory predict that inside a black hole, these extra dimensions could influence how matter and energy behave, potentially offering a way to unify gravity with quantum mechanics. Another promising approach is loop quantum gravity, which suggests that space-time itself is made up of tiny, discrete units, much like pixels on a screen. If this is true, then singularities inside black holes might not truly exist. Rather, they could be replaced by a quantum structure that avoids the infinite densities predicted by general relativity. Some researchers even propose that what we call a singularity might actually be a wormhole, leading to another region of space-time or even another universe. As we continue to study black holes, through gravitational wave detections, simulations, and the Event Horizon Telescope, which captured the first image of a black hole, we may inch closer to answering some of the biggest questions in physics. Could black holes be nature's laboratories for testing a quantum theory of gravity? Will they finally bridge the gap between relativity and quantum mechanics? Until we solve these mysteries, black holes will remain the most enigmatic objects in the universe, holding secrets that could redefine our understanding of reality itself. Time is one of the most elusive and mysterious aspects of the universe. While we experience it as a steady, unchangeable flow from past to future, physics tells a different story. In Einstein's theory of relativity, time is not a separate, absolute entity, but is woven together with space to form space-time, a four-dimensional continuum. The passage of time is relative, meaning it changes depending on gravity and velocity. This effect is most dramatic near black holes, where gravity is so strong that it significantly distorts time itself. If you were to orbit near the event horizon of a black hole, time would pass much slower for you compared to someone far away. This means that if you spent a few minutes near a black hole, centuries could pass for the rest of the universe, a phenomenon known as gravitational time dilation. At the quantum level, time becomes even stranger. Unlike in relativity, where time is continuous and smooth, in quantum mechanics, time behaves in a much more uncertain and probabilistic way. According to some theories, time may not even be fundamental. It could emerge from a deeper quantum reality, much like temperature emerges from the movement of molecules. One of the biggest unresolved questions in physics is whether time is truly fundamental or if it is simply an illusion created by our perception. In the realm of quantum gravity, where scientists attempt to unify Einstein's relativity with quantum mechanics, time does not always play a clear role. Some theories suggest that time itself may disappear at the smallest scales, meaning that the universe may not evolve in a way we intuitively understand. Another mind-bending concept is the idea of a block universe, a theory in which past, present, and future all coexist simultaneously. According to this view, time does not flow but instead exists as a complete structure, where our perception of moving through time is merely an illusion. This challenges our deepest intuitions about reality and raises profound questions about free will, destiny, and the nature of existence. As physicists push the boundaries of understanding, new theories such as loop quantum gravity and string theory suggest that time and space might be emergent properties of an even deeper reality. Perhaps space-time itself is not continuous, but is made of discrete quantum units, just like matter is composed of atoms. If true, this could revolutionize how we think about black holes, the origins of the universe, and the fundamental nature of reality itself. The study of time, and its relationship with black holes, quantum mechanics, and the universe as a whole, is one of the most exciting frontiers in physics. Will we one day discover that time is an illusion? Could we manipulate or even travel through time using the strange properties of black holes? As we uncover more about these cosmic mysteries, we may be forced to rethink our very understanding of what it means to exist in the universe. Black holes are among the most fascinating and enigmatic objects in the universe. These cosmic behemoths, formed from the remnants of massive stars that have collapsed under their own gravity, possess gravitational fields so strong that nothing, not even light, can escape their grasp. This makes them invisible to traditional telescopes, but their presence can be detected by observing the behavior of nearby matter and the warping of space-time. At the heart of a black hole lies the singularity, a point where gravity becomes infinite and the known laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. Crossing this boundary means being forever trapped in the black hole's grip, spiraling toward an unknown fate. One of the greatest mysteries of black holes is what happens to information that falls into them. According to classical physics, anything that enters a black hole is lost forever. However, quantum mechanics suggests that information cannot be destroyed, a paradox known as the black hole information paradox. Some theories propose that information may be stored in the event horizon or even leak out over time as Hawking radiation, named after physicist Stephen Hawking, who discovered that black holes slowly evaporate. Even more mind-boggling is the idea that black holes could act as gateways to other universes. Some physicists propose that falling into a black hole might not lead to destruction, but instead could transport matter into a parallel universe or another region of space-time. This concept is closely linked to wormholes, theoretical tunnels that could connect distant points in space and time, potentially allowing for faster-than-light travel or even time travel. The study of black holes is pushing the boundaries of our understanding of physics. With new observations from the Event Horizon Telescope, which captured the first ever image of a black hole's shadow in 2019, and upcoming advancements in gravitational wave astronomy, we are beginning to unlock the secrets of these cosmic monsters. But as we probe deeper, black holes continue to challenge our perception of space, time, and reality itself. The warping of space-time, how black holes bend reality. One of the most mind-bending effects of black holes is their ability to warp space and time itself. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time, much like a heavy ball placed on a stretched rubber sheet. Black holes, with their immense gravity, take this warping to the extreme, creating regions where time slows dramatically and space is twisted beyond recognition. This phenomenon, known as gravitational time dilation, means that time moves slower the closer you get to a black hole. If an astronaut were to orbit just outside the event horizon while their twin remained far away, the astronaut would experience time at a significantly slower rate. When they returned, they would find that their twin had aged far more, an effect predicted by relativity and confirmed in experiments involving high-speed travel and strong gravitational fields. Beyond merely slowing time, black holes also bend light, a process called gravitational lensing. Light passing near a black hole is bent around it, sometimes creating multiple images of the same object or even forming a circular halo known as an Einstein ring. This effect allows astronomers to detect black holes and distant galaxies otherwise hidden from view. At the most extreme level, black holes may contain closed, time-like curves, theoretical loops in space-time that could make time travel possible. If such curves exist, they might allow objects or even information to travel back in time, though how this would work in practice remains one of the greatest mysteries of modern physics. The warping of space-time by black holes is more than just a theoretical concept. It is a phenomenon with profound implications for our understanding of reality. As scientists continue to study these enigmatic objects, they may uncover deeper insights into the nature of time itself, the limits of relativity, and the possibility of harnessing the warping of space-time for interstellar travel. Black holes are not just cosmic vacuum cleaners that swallow everything in their path. They also challenge our fundamental understanding of physics. One of the greatest mysteries surrounding black holes is the information paradox, a problem that pits quantum mechanics against general relativity. In physics, the principle of conservation of information states that information about a system's initial state can never be completely lost. However, when something falls into a black hole, it seemingly disappears forever, erased from the universe once it crosses the event horizon. According to Einstein's equations, anything that enters a black hole is crushed into the singularity, an infinitely dense point where the laws of physics break down. But quantum mechanics suggests that information should never be lost. It can be scrambled, hidden, or transformed, but never completely destroyed. This contradiction is known as the black hole information paradox, first highlighted by Stephen Hawking in the 1970s when he discovered that black holes slowly evaporate over time through a process called Hawking radiation. This radiation causes black holes to shrink and eventually disappear, raising a troubling question. If a black hole completely evaporates, where does all the information about what fell into it go? If it vanishes, that would break the laws of quantum mechanics, shaking the foundations of modern physics. Physicists have proposed several possible solutions. Some theories suggest that information is encoded in Hawking radiation itself, though we don't yet understand how. Others propose that information is stored on the event horizon, in a way similar to a hologram, an idea linked to the holographic principle, which suggests that the entire three-dimensional universe might be a projection of information stored on a distant cosmic boundary. A more extreme idea is that when black holes disappear, they leave behind Planck-scale remnants, tiny stable objects that store all the lost information. Alternatively, some researchers suggest that information may escape through wormholes or be transferred into a parallel universe. The resolution of the information paradox could lead to groundbreaking discoveries about the nature of space, time, and reality itself. If black holes truly destroy information, we may have to rethink the most fundamental principles of physics. If information survives, it could reveal entirely new aspects of quantum gravity and the fabric of the cosmos. One of the most mind-bending aspects of black holes is their ability to warp time itself. According to Einstein's theory of general relativity, gravity isn't just a force, it's the curvature of space-time caused by mass. The more massive an object, the greater its gravitational pull, and the more it distorts time. Black holes, with their immense gravitational fields, create the most extreme time dilation in the universe. The closer you get to a black hole, the more time slows down relative to an outside observer. This effect, known as gravitational time dilation, means that an astronaut falling toward a black hole would experience time differently from someone watching from a safe distance. If an observer were watching from afar, they would see the astronaut moving slower and slower as they approached the event horizon, appearing to freeze in time just before crossing it. However, to the astronaut themselves, time would pass normally. This phenomenon raises profound questions about the nature of time. Could black holes act as natural time machines, allowing for extreme time travel into the future? If someone could hover just outside the event horizon without being torn apart by tidal forces, they could experience time much more slowly than the rest of the universe. By the time they returned, millions or even billions of years might have passed elsewhere. Some physicists even speculate that if a black hole connects to a wormhole, it might be possible to use its time-warping effects for travel across space-time. However, these ideas remain highly theoretical, as no known force could prevent an object from being crushed by the overwhelming gravity of the singularity. The study of black hole time dilation isn't just a theoretical curiosity, it has practical implications for understanding the fundamental nature of time. If time can be stretched or slowed to such extremes, it raises deep questions about whether time is an absolute property of the universe or something more flexible and relative than we ever imagined. One of the most perplexing mysteries in modern physics is the black hole information paradox, a problem that challenges our understanding of quantum mechanics, general relativity, and the fundamental laws of the universe. At the heart of this paradox is a simple yet profound question. What happens to information that falls into a black hole? In classical physics, information can never be truly destroyed. Even if you burn a book, the atoms and energy still exist in some form, scattered as heat and light. However, black holes pose a problem. According to Einstein's general relativity, anything that crosses the event horizon is lost forever, unable to escape, even light. If this were the case, any information that enters a black hole should also be lost. This clashes with quantum mechanics, which states that information can never be destroyed, only transformed. The fundamental principle of unitarity in quantum physics demands that if we knew the exact state of a system, we could, in theory, predict its past and future. But if black holes erase information, this principle breaks down, leading to a major contradiction in physics. In the 1970s, Stephen Hawking made a groundbreaking discovery. Black holes slowly evaporate over time due to a quantum effect called Hawking radiation. This process suggests that black holes do not last forever. They shrink and eventually disappear. The problem? Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. If true, this would mean information is lost from the universe, a violation of the fundamental laws of physics. This paradox has puzzled physicists for decades, and several possible solutions have been proposed. Some physicists suggest that information is not lost, but rather stored in a holographic manner on the surface of the event horizon, an idea supported by the holographic principle. Others propose that subtle quantum effects allow information to gradually escape through Hawking radiation in a highly scrambled form. Another radical idea is that black holes could be gateways to other regions of space-time or even other universes, allowing information to escape in ways we don't yet understand. Some researchers propose that intense radiation, called a firewall, destroys anything that falls into a black hole, potentially resolving the paradox but contradicting general relativity. Despite these theories, no definitive answer exists yet. Solving the information paradox may require a new theory of quantum gravity, one that unites Einstein's general relativity with quantum mechanics. Understanding black holes might not only reveal what happens to information, but also provide deep insights into the very nature of space, time, and reality itself. Some physicists believe that the solution to the black hole information paradox lies in the concept of quantum entanglement. In this view, Hawking radiation is not entirely random. Rather, it is subtly entangled with the information that originally fell into the black hole. If this is true, then information is not lost, but instead encoded in a highly complex and scrambled way within the outgoing radiation. This idea is supported by research into quantum information theory, where scientists have found evidence suggesting that the information might leak out of a black hole in a way that preserves the laws of quantum mechanics. Another promising approach comes from the ADS-CFT correspondence, a concept from string theory that suggests a deep connection between gravity and quantum field theory. This principle implies that everything happening within a black hole might be fully described by a lower dimensional holographic representation on its surface. In essence, the three-dimensional interior of the black hole could be encoded on a two-dimensional boundary. If this is true, then information is never lost. It merely exists in a different form than we previously understood. Some researchers take even more radical perspectives. The idea of black hole complementarity, for example, suggests that information can both fall into the black hole and remain outside it simultaneously, depending on the observer's perspective. This would mean that no single observer ever sees a violation of quantum mechanics, avoiding paradoxes. However, this explanation remains controversial and lacks direct experimental support. More recently, breakthroughs in quantum gravity research suggest that black holes might not be completely sealed-off entities. Instead, they could be connected to the rest of the universe in subtle, unexpected ways. The concept of wormholes, tunnels in space-time that could link one region of the universe to another, has gained traction as a possible resolution. Some scientists propose that black holes and their outgoing Hawking radiation are connected through tiny quantum wormholes, allowing information to escape in ways that were previously unimaginable. Understanding them may ultimately lead to a unification of quantum mechanics and general relativity, bridging the gap between our understanding of the very small and the very large. The search for this unification is one of the greatest challenges in modern physics, and black holes may hold the key to unlocking the deepest secrets of reality itself. If black holes truly hold the key to unifying quantum mechanics and general relativity, then understanding their nature could revolutionize physics. Some of the most cutting-edge research now focuses on quantum gravity, an area that aims to merge Einstein's theory of general relativity with the probabilistic world of quantum mechanics. Theoretical approaches like string theory and loop quantum gravity suggest that space and time may not be continuous, but instead made up of tiny, discrete units. One of the biggest breakthroughs in recent years has been the realization that space-time itself may emerge from quantum entanglement. If this is true, then black holes could provide a testing ground for this radical idea. Their extreme conditions might reveal that space-time is not a fundamental construct, but rather a byproduct of deeper quantum processes. Furthermore, the information paradox challenges our understanding of causality and time itself. If information escapes a black hole in a scrambled but recoverable way, then the very fabric of space-time might behave differently than we expect. Some theories propose that black holes could be gateways to understanding how time flows, whether it is truly linear, and if the past can influence the future in ways we have yet to grasp. The search for answers continues, with major experiments and observations pushing the boundaries of our knowledge. The Event Horizon Telescope has already provided the first images of black hole shadows, and future telescopes may be able to test some of these groundbreaking theories. Advanced gravitational wave detectors are also improving our ability to study black hole mergers, offering new insights into their properties and behavior. Ultimately, black holes remain one of the most profound mysteries in the universe. They challenge our understanding of physics at every level, forcing us to rethink fundamental concepts of space, time, and reality itself. Whether through quantum information theory, holography, or entirely new frameworks yet to be discovered, the study of black holes is likely to reshape our view of the cosmos in ways we can barely imagine. If black holes are the key to a deeper understanding of physics, then their role in shaping the universe is just as profound. These cosmic giants do not merely consume matter, they also influence the evolution of galaxies, regulate star formation, and may even play a role in the ultimate fate of the universe. Supermassive black holes at the centers of galaxies shape their surroundings through powerful jets and intense radiation, controlling how gas cools and condenses into new stars. The balance between these processes determines whether a galaxy thrives or fades away into darkness. On a grander scale, black holes may hold clues about the very structure of the universe. Some theories suggest they could be linked to dark matter, the invisible substance that makes up most of the universe's mass. Others propose that black holes may serve as cosmic seeds around which galaxies and larger structures form. The possibility that they could be connected to wormholes or even alternate universes continues to be a subject of speculation and intense research.